So we have learned about flow lemma. And our plan is to combine the regularity lemma and the blob lemma together to obtain results about Dirac type Kesem. We are finding large graph, spanning graph, or near spanning graph. And the issue for that is that if you apply the regularity lemma, then you get the regularity partition. And the issue is that it's not super regular. So the pairs are epsilon regular, but not super regular. And also this R, this graph, has large max degree. And usually the number of parts is much smaller than epsilon. But this later part is not too problematic. You can just take a subgraph of reduced graph. So we take an appropriate subgraph of R with a bounded maximum degree. That's okay. And first one, for that, I mean, we need to collect some property. So one property is that, let's assume that, again, epsilon is more. If you have a epsilon d regular pair, AB in G, then you can find the subset such that the, how do I say it? So A prime has at least size like 1 minus epsilon times A, and B prime has size at least 1 minus epsilon times P, and this A prime and B prime is 2 epsilon B superregular. So in fact, what you can do is you have you collect all the vertices with the 2 low degree, then you show that the number is not so many, and then you just delete them. So this is true. And also, I mean, what you can show is that when you have an epsilon regular pair A and B, deleting small number, I mean, the remaining thing is still epsilon regular. And even adding some vertices, you take say, symmetric difference of this. So you take a symmetric difference for, say, A prime and B prime has small size. And the resulting one is again the epsilon regular. Yep. So we can freely delete or add vertices while not ruining the epsilon regularity too much. And in order to make this super regular, you additionally make sure that the degree conditions are satisfied. Anyway, this we know. From here, what we can obtain is that if you have a epsilon regular partition, and your R has a bounded maximum degree. So your reduced graph. So here, what's reduced graph? So this is your reduced graph. And then this G has the corresponding partition. And applying this, you can delete the small number of vertices that has 2 row degree to this direction and 2 row degree to this direction. And 2 row degree to this direction and 2 row degree to that direction every time. So for this vertex, you consider all the neighborhood, so all the epsilon regularity partition, epsilon regularity pi graph, and then you delete the vertices which has 2 row degree here, delete the vertices with 2 row degree here. Then what you can get is that let's say you have B1, B2, B3, B4, B5, B6, B7, so that there is UI subset of BI with say size UI being, okay, let's say in this way. For any, say, every BI has size M, say, for any M prime, which is between, say, 1 minus 3 delta M and 1 minus 2 delta M. And you can find the UI for each I. Such that this UI has exactly M prime vertices. I mean, it's actually the number of vertices that you want to make it between here and here. And now the remaining one is epsilon t plus superregular. So let's not say epsilon. It's getting worse, but say like 10 delta epsilon pi. For every ij in the reduced graph. So basically, as long as your reduced graph has bounded maximum degree, then you can kick out small numbers from each part, and then make sure that your regularity partition is superregular one. And all the deleted one, you add it to B0, but this is still small. The number here is still, originally it's most M epsilon n, and we kick out most like 3 delta fraction from each one. So now it's like 3 delta plus 1 epsilon n almost. And in order to find the spanning copies, you have to also distribute this. You have to also use this vertex because your H and G have exactly the same number of vertices. So every vertex in this G has to be mapped from a vertex in H. And what you do is each one of them, you decide where to move. If this one has the lots of edges to here and lots of edges to here, if, I mean, that happen, if this specific vertex has many edges here, and this can go to here. So you move it to here so that after adding it, this vertex still has lots of neighbor and lots of neighbor, so it will be okay. And we will, I mean, in order to do that, we have to show that every vertex here can go to somewhere so that these are superregular. And the number of vertices in each one of them is exactly at V1 peak. Because H already have a specific structure, right? H looks in such a way that we have to embed this to here, this to here, this to here, this to here, this to here. So that we have to make sure that this and this has exactly the same number of vertices. So that distribution is something that we have to do. Usually it's not not too easy, but not too difficult to make this distribution. Sure. And with this kind of picture in mind, I mean, we can show that this kind of lemma is useful. So I didn't write down the full statement, but based on what I explained, I believe that you have understand what this is saying. And another useful lemma is that so again, if you have a reduced graph R of this G, this is a epsilon delta reduced graph of the partition, epsilon regular partition. Then what we know is that this R inherits the minimum degree condition on N, on G. If it has the, say again, this holds, and yeah, maybe I will write down the statement. I wanted to actually avoid writing down, but it will take similar time. So that's B0, B1, BR, be on epsilon regular partition. So what was the epsilon regular partition? So the one that we obtained from regularity lemma. So we know that each BI has the same size. Then B0 has the size at most epsilon n. And for each I, there are at most epsilon r indices J such that G, Bi, Bj is not epsilon regular. So for each vertex, for each cluster, it is epsilon regular with together with the other Bj for most of the J. So that's the epsilon regular partition we are gonna talk about. So whenever we say epsilon regular partition, we consider this condition. So if you recall to the regular lemma, we have R1, R2, R3, three conditions. Third condition, weaker condition is that and most epsilon fraction of the pairs are not epsilon regular, but we assume the stronger condition that for each I, there are at most epsilon times R indices J such that Bi, Bj is not epsilon regular. Okay, then this is the regular partition. And then what we know is that if minimum degree of G at least D plus 2 delta N, then minimum degree of R is at least Dn. So the loss on the minimum degree is not big. Okay, knowing that, let's see how we can use this blob lemma. So there is this conjecture called Alon-Yuster conjecture, and then it's proved by Komros-Sarkozy and Semoredy. Alon-Yuster conjecture, which is proved by Komros-Sarkozy and Semoredy in 2001. So for given k-partite, the F vertex graph F. Let me write it this way. So again, n is small, and say C is some large constant which only depends on K and F. Then if on n vertex graph G satisfy minimum degree at least 1 minus 1 over K times n plus C, and n is a multiple of F, then G contains an F vector. So here F vector is the disjoint union of F, disjoint union of copies of F that covers all the vertices in G. And we can prove an approximate version of this by using low lemma. So in the same setup, let's say you have a slightly bigger minimum degree condition, and then we want to, again, you assume that the n is large, then we want to show that the G contains at least 1 minus alpha times n over f copies of vertex disjoint copies of f. So let's prove this. So whatever your f is, it has it is k part type graph. So it has, its chromatic number is n mod k. Then what? Let's say this is your f. So let's say your k is 3. And this is your graph. Then now it has what? 1 vertex here, 2 vertex here, 3 vertex here. So it doesn't have a equitable partition. But what you do is you draw this one more time with the 1 vertex here and 2 vertex here, and then draw this one more time here, and then you take a union of 3 of them, and then put it this way. So this is this connected graph, and then let's say f prime is the union, and this has a equitable partition. So let f prime be its joint union of k copies of f. Then it has a vertex partition x1 to xk such that each xi has size f, and this is independent set. So let's choose delta so that what? Delta and epsilon this here n is chosen so small so that even if you apply external regularity lemma, the number of partitions will be still much smaller than n. So we apply regularity lemma with say parameters epsilon, and say your t is epsilon to negative 2, so which is the minimum number of parts in your Lagrange graph. And then we obtain an epsilon regular partition E0, E1, ER, with this R is still much smaller than n, but R is much bigger than what? T. Then what? We consider an epsilon delta reduced R on this partition. Okay, and let's say let M be the number of parts, number of vertices in each cluster. And what? So by moving vertices from sum of B R minus K plus 2 to say B R to B0 if necessary, we can assume that the K divides R. And we may assume that B0 still have at most 2 epsilon and vertices. So initially this epsilon regular partition, so B0 exceptional vertices. The number of exceptional vertices is at most epsilon n, but how many we have added? So at most K minus 1 times 1 over R times n more vertices. And this is at most n, epsilon n, because R is bigger than T, which is what? 1 over epsilon square. So this is still small. And each m is what? Between 1 plus minus 2 epsilon n over R. So it's at least n, 1 minus 2 epsilon n times n over R, and n most n over R. So now what? Now what we want to do is that in this epsilon regular partition, we will forget the old edges inside here, and we will forget the old edges between not epsilon regular pairs, and we will forget the edges between the pairs which are two sparse. So so if ij is not in R, then what? It's either Bi, Bj, the bipartite between is not epsilon regular, or it has density less than delta. So those edges we will forget, and then we only use the edges here with the ij in this ER. Then from the previous lemma to this lemma, but by the way, this whole lemma that I introduced are relatively easy from, the definition of regularity, so you can prove it for yourself. And by that, we know that the delta of R, the minimum degree of R is at least what? So this subtract 2 delta here, but delta is much smaller than alpha, which is much bigger than 1 minus 1 over K times R. So we can apply final Semoledi theorem. The final Semoledi theorem implies that we can partition this bracket R into R over K vertex disjoint copies of KK in R. And now we use the lemma say this lemma star. So it's KK. So this is disjoint union of KK. That's your R here. And that has maximum degree at most delta. So we can invoke this lemma. In other words, for each parts, if this is your KK, for each BI, you choose all the vertices which has 2 row degree to here, or 2 row degree to here, 2 row degree to here, then you can delete. And then if you want, you can delete a bit more to make sure that the number of vertices here is exactly as you want it. By lemma star with this R prime, let's say, let R prime be this KK vector in R. Then applying this lemma to R prime, which is the union of vertex disjoint coefficient of KK, then what? We can find UI in each VI such that all of them at size exactly m prime, it's exactly 1 minus 3k epsilon n. Okay. And each UI uj is 6k epsilon, say 10k epsilon, comma delta plus superregular. For all ij in this R curve. And we put the vertices in not included in UI to B0, then it is B0 has size at most say 3k epsilon n. Okay, now what? You let this F double prime be, say, how many disjoint union? So let's say this many. M prime over the number of vertices in F prime. F prime has what? KF vertices. This many disjoint union of the copies of F prime with the an equitable partition. The x prime 1 to x prime k. And by using blow lemma, what? We can embed this F double prime into the G of the BK, where this BK is the union of BI, where I is in K, and this capital K is a clique in R. So we do that for each capital K in R prime. Then what? How many copies have we do that for each one of them, then how many copies did we get? So this many, and for each of, we do that R over K prime. So this many copies of F prime, so that give you M prime over K F times the R copies of F, because this is disjoint union of K copies of it. But what we know that F prime is roughly this 1 minus 3K epsilon and over R, sorry, over R, and then you take 1 over F and then R, and you get what? So that's the number of copies that you get. So you get at least this many copies. Where did we make mistake? It seems that I have made a mistake. Which F prime has M prime over Fk copies. No, you use K copies, so this is not here. So you use all together what? In each click capital K, you have a K times M prime vertices. Then you pack. Yeah, so you can pack this many disjoint copies. And here, and then you can get the answer here. And due to our choice, this is bigger than 1 minus alpha n over F, because epsilon is much smaller. So this will be the proof of what we wanted to prove. So this was a simple illustration of how we can use this problem to find the large subgraph in your graph G. But this was particularly easy because our graph that we want to find was not spanning. So there was some room, so we could delete some vertices, and then we just move it to exceptional vertices, and those we can just ignore it. So it was easy, and then it was easy because this was totally disconnected. Because every component in your F vector, I mean, there are many components. It's totally disconnected, so you can freely decide where to put it, right? And because of that, the R prime you take, which we obtained from Heiner-Demory theorem, was already sufficient for our purpose. But what if we want the spanning copy of connected graph, such as Hamilton cycle? Of course, for Hamilton cycle, Dirac theorem already gives us the answer on the minimum degree condition. There are certain other, theorems. For example, you can consider case power of Hamilton cycle. So what's case power? So this is the graph where we add an edge between any vertices with the distance and mod u. The distance between u and v in G is m mod k. So for Hamilton cycle, so h to the 1 is Hamilton cycle itself. H squared is you have to add these edges. And h cubed is you have to also add this edge. And so on. And there are famous conjecture, Both-half conjecture, said that if your minimum degree of your graph G is at least 2n over 3, then it contains G contains a square, the square of Hamilton cycle. And there is CMOL conjecture. That's that if your minimum degree is at least 1 minus 1 over k plus 1, and then G contains the case power of Hamilton cycle. And together, I mean, it's called Posa-Simons conjecture. So it is 1962 and 1974. And 콤로스 알코올 때문에디 prove both conjecture. And they use the regularity lemma and flow lemma. I mean, for sufficiently large n. And there is a conjecture that kind of incorporates this kind of a statement, which is called the bandwidth theorem. So so what is it? So in order to talk about this, let's define separability. So n vertex graph H is eta separable if it contains a set S which has size m of a pi n, such that once you delete it, then it totally disconnects the graph in the sense that its component of H minus F has size m of a pi n. Okay. And what's bandwidth? Bandwidth of graph G is the minimum B such that there exists an ordering B1, B2, Bn of the vertices in G such that Pi and Pj are adjacent implies difference between I and J is M of P. So this is if we check the ordering and then try to measure the distance of this edge adjacent vertices, and we choose the maximum distance in each ordering, and then you consider all the orders which minimize B, and that's the bandwidth. So both concepts are loosely equivalent in for bounded maximum degree graph. If your graph has bounded maximum degree, then the small separability, a little of one separability, implies little of n bandwidth. And little of one bandwidth implies the little of one separability. So If it's the same situation as before, if you have epsilon separability, then it implied f of epsilon and bandwidth. And if you have epsilon and bandwidth, it implies g of epsilon separability. Technically, you have to put the delta into the function as well. So this is only for bounded one. Anyway, so because of this, I mean, these two concepts are almost equivalent. So that usually, people use this notion to take the bandwidth theorem, but I will use this one to take it because it will more fit to the proof that we will, explain later. So Bocher and Schacht and Taraz prove a conjecture by Bolovas and Komlos, which is now called the bandwidth theorem. So for given k and delta and alpha, there exists the eta positive and n0. Okay, let's again write it this way. So assume so you have 1 over n eta, which is much smaller than the alpha 1 over k and 1 over delta. So the positive. So this is same as saying for given alpha and k delta, there exists the eta 0 and n0 such that n is bigger than n0 and then eta is smaller than eta 0, then the following statement holds. So if H is an n vertex graph with a chromatic number k and its maximum degree is bounded and H is eta separable. So separability is something like having not too high connectivity, somewhat low connectivity. And if she is on n vertex graph with minimum degree at least 1 minus 1 over k plus alpha times n, then she contains H as a doublet. So this pretty much includes the theorems in the previously introduced Dirac theorem up to some error term. So this shows that if you have a H which has bounded maximum degree and then which has low connectivity, then its chromatic number pretty much indicates the minimum degree threshold for having it. But you might think that if n is odd, then what? H is Hamilton cycle. But its chromatic number is 3. But the Dirac theorem says that half n is the threshold. So you might think that this might not give you the approximately optimal one for this case. But this graph is almost bipartite. If you delete one vertex, it is bipartite, right? So actually, there is a more technical version of this theorem saying that if you have H and satisfying this, but instead of K chromatic, you delete very little number of vertices, which is not too scattered. Yeah, then this is still true. So that's what you can prove from. There is a more technical version that also covers this. But here, you just delete one vertex and it is bipartite, right? So instead of being K chromatic, you delete very small number of vertices, and then this is still bipartite. No, then it becomes K-chromatic and it is okay. Technically, it's not just very small number of vertices, and then those small number of vertices has to be not so scattered in your bandwidth ordering. It's somewhat cluttered somewhere so that but I will not talk about too much technical detail of the statement. But this give you a more general framework for, more general statement regarding the minimum degree threshold for having certain spanning subgraph. Of course, for specific subgraph, this might not be tight. There are as I shown here, there is 3 chromatic graph, which whose threshold is lower than 1 minus 1/3. You can come up with the other graph, which I mentioned that there is more technical statement that also includes this in this bandwidth theorem, but you can still come up with the other graph, which does not satisfy that technical condition. And still this is 3 chromatic, and the optimal value is somewhat between half and 2/3 n. So for specific graph, this theorem does not give you the tight one, but in general, if you consider all chromatic number graph, K chromatic graph, then this is best possible. Because without epsilon, this is the type bound for having KK factor. So that's what we have seen from the Heiner-Femerdi theorem. And that Heiner-Femerdi theorem is tight. So roughly what it says is that if you have an n vertex K chromatic graph, and then bounded maximum degree, and your connectivity is not high, then embedding H into G is just as hard as embedding KK factor into G. It's not much harder than embedding KK factor into G. Okay, so yeah. So next time I will prove this for the case where case 2. And then that will give you some idea on how one can use the blow lemma to prove this theorem. Okay, then thank you for listening. I will see you in the next video then.